This lesson we'll be learning about how to calculate bond energies. You've seen this table of bond energies before, but I'd like to explain a little bit more about it and then show you how it is useful. Experimentation has been done to see how much energy is required to break a covalent bond between two atoms. As you're aware, unbonded atoms have 0 kilojoules of energy. It is the most amount of potential energy that an atom or molecule can have. It is the top baseline. And when molecules form bonds, they fall down the well and become more stable and lower in potential energy. The amount that they lower in potential energy is the amount on our table of bond energies. Experimentation was done to see how much energy it takes to break a bond in a molecule for 1 mole of that molecule. And consequently, the amount of energy that is needed to break a bond is also the amount of energy that is produced when a bond is formed. It's the same amount in as it is out. So our table of bond energies represents how much energy is needed to break a bond and how much energy is produced when bonds are formed. With this information, we can calculate the overall amount of energy needed for a reaction or the overall amount of energy that is produced from a reaction. And that would be graphs that you've seen before, like this, where the potential energy of the products is lower than the potential energy of the reactants, and this reaction produces energy overall. Or reactions where the product's potential energy is higher than the reactant's potential energy, and this reaction requires the input of energy to proceed. So you can calculate overall energies of reactions from bonding energy because everything is cumulative. So let's look at an example. This is the reaction that we did at the beginning of the year where we set off our rockets. So let's look at the amount of energy that it either produces or requires. As you can probably guess, this reaction produces energy because it made our rockets explode or fly. Let's do some calculations. First step is to draw the bonds so you know what you're looking at. H2 is 2 hydrogens bound together, and the bonding energy of this is 430 kilojoules per mole. And based on our balanced chemical equation, we have 2 moles. So the amount of energy for this here is 860 kilojoules, and multiplied it by 2. The next is oxygen. Oxygen is doubly bound. You should know that from being able to do Lewis dot structures. And if we find double bound oxygen, it is 500 kilojoules. For the reaction side, we add these energies together to get the total amount of energy that is needed to break all the bonds in the reaction. 1,360 kilojoules are needed to break all the bonds. So we have to break the bonds here, here, and here. Once the bonds are broken, they can reform into water. So we draw water, and we have 2 of them. So you can either multiply by 2 or you can draw them out like this. And then we look at each bond separately. Each water molecule has an OH bond, and that's 460 kilojoules. So this one's 460, and this one's 460, and this one's 460, and this one's 460. And if we add all of those 460s up together, we get 1,840 kilojoules produced. You should see here that the amount of energy we're producing is more than the amount of energy that is needed to break all of the bonds. So overall, this reaction produces energy, and it produces 480 kilojoules per mole of energy. If we were to draw the graph of that, it would look like this. So up here, because we're going lower, so we've got negative 1360 kilojoules, and then below that negative 1840 kilojoules, making them negative because this is potential energy. So we have our reactants here, and then we go down, and we have our products here. So we can write on here H2 plus O2 and 2H2O, and this difference from top to bottom here, known as delta H, is 480 kilojoules per mole. You can visualize that the energy is on the product side because it's being produced by the reaction. If this were an endothermic reaction where the amount of energy of the products was higher in potential energy than the products, than the reactants, then the energy number would go over here. All right, see what you can do.